Here we have a simplified version of a solar cell, and we have right here our semiconductor silicon layer. On top of that is adhesive, and then we have glass. And what we need to find out is the temperature of the silicon that we're going to call T1, as well as the temperature at the surface that we're going to call T3. So since we have heat traveling through different materials and through different modes, we can draw a thermal circuit and use the resistances to solve for our temperatures. So we're going to use as our governing equation that Q equals delta T divided by the sum of the resistances between those two temperatures. And in our case, we're going to say T1 minus T infinity, where T infinity is the temperature of the air, or 25 degrees C, is going to be the sum of the total resistances between them. So if we're trying to find T1, that's going to equal our Q times our total resistances plus T infinity. Let's start by looking at a thermal circuit for the process. We're going to start with the silicon, which is at T1. And now going between the silicon, we have a resistance that's caused by the adhesive, and we get to T2, which is at the top of the adhesive. Then we have a resistance that's caused by the glass. Then we have the temperature of the surface. And then we have two resistances in parallel. One is caused by the radiation, and this is T surrounding. And the other is caused by the convection, and this is T infinity. And both T surrounding and T infinity are 25 degrees C. So let's look at what these resistances are. The conductive resistance is L sub A, the length of the adhesive, divided by its thermal conductivity times the area. Here we have L sub G divided by K sub G times the area. Here we have the resistance of the radiation, which was given to us in the problem. And here we have 1 over the heat transfer coefficient for convection times the area. So we solved for H in a previous screencast, so we can write this entire circuit out in terms of our total resistances. Our total resistance is LA divided by KA times the area, plus L sub G divided by K sub G times the area, plus 1 over HA plus the resistance of the radiation, and since these two are in parallel, this is to the minus 1. Let's list what we know. So let's put these into our equation for the total resistance and solve. We get a total resistance of 0.54 Kelvin per watt. So our T1 is going to equal our Q times this total resistance plus T infinity. So our T1 is going to equal 352 Kelvin. So now we need to find T3. So what we do is we go back that our Q equals delta T times the sum of the resistances between them. And now we're going to set it up as T1 minus T3. And the two resistances between them, let's go back and look at this thermal circuit. The two resistances between T1 and T3 are the two conductive resistances. So this is going to equal the sum of the conductive resistances. And now we can write that T3 equals T1 minus Q times this R. Let's calculate what our conductive resistances are. They're L sub A divided by K sub A times the area, plus L sub G divided by K sub G times the area. This equals 0.0286 Kelvin per watt. And now we have the necessary information that we need. And our T3 is going to end up equaling 349 K. And this is exactly what you would expect. The temperature of the silicon should be the highest, followed by that surface temperature. The surface or the temperature in between the two, if you take a look at our picture, this T2 should be somewhere in between 352 and 349 K, and these are all greater than the surrounding air, which is 298 K.